Hey, before we continue, please consider subscribing to two excellent channels about IT, Avocodus and AveTech. Avocodus is a great channel with programming tutorials and IT humor, and AveTech is about the stories behind tech and business. Links are in the description. Thank you.
In this Introduction to Stochastic Models video, I'm going to talk a little bit about different kinds of stochastic models and different kinds of stochasticity and what they mean, particularly in terms of population models. First, let's quickly get straight the difference between deterministic models and stochastic models. In a deterministic model, everything in the model is determined from the beginning. Every time you run the model, it'll come up with the same results. Let's say I have my deterministic population growth model, n at times t plus 1 is equal to n at times t times some growth rate lambda. This is a deterministic model because if I know what lambda is, and I know n at time any t really, because if I know lambda and n at times t, it tells me all of the possible n at t's into the future, and I can extrapolate backwards in time as far as I want, forever. The whole process is determined. A simpler way of thinking of deterministic models is that nothing in them is random. Right, so that's a pretty standard deterministic population growth model. A stochastic model is any model that has some element of randomness to it. Every time you run a simulation of the model, it will come out different because somewhere in there is a random process. For example, the stochastic equivalent of this model would be to say n at times t plus 1 is equal to n at times t times lambda t, the growth rate at times t, where lambda at time t is drawn from some distribution, some random, well, not some random, but some probability distribution every time t. So let's say lambda, in this case, we'll just make it normally distributed with a mean of, I don't know, 1.2 and a variance, say, 0.02. So it's small. There's not a lot of noise, but it's some noise. So what does it matter if we add randomness to our models? Well, just for a quick comparison, if I actually ran models like this, a deterministic exponential growth model and a slightly stochastic one, what you'd see is that for any initial population size n, the deterministic model, lambda is 1.2, so it's going to grow pretty quickly and exponentially. So that's my deterministic model. If I use the stochastic model, every time step, my population is going to grow on average at a rate 1.2, but not always exactly 1.2. So sometimes it'll grow, sometimes it'll shrink, and you get a little bit of noise. And because I set the variance to not be very big, right, most of the time you'll get trajectories that are pretty close to the deterministic case. But in any stochastic model, even if the variance is small, it's always possible for weird things to happen, like population extinction. You just might get a bad run. Or you might get a huge population explosion. A fairly unlikely event, but still possible. So stochastic models let us ask all kinds of interesting questions about our system that deterministic models don't allow. Like, interesting stuff happens, like, what's the probability of extinction in a population with these growth parameters? Or what's the probability of extinction in the next 100 years? Before the year 2100. Or what's the probability that n is going to be greater than 1 million by the year 2100? In a deterministic model, I can tell you what my population size will be at any given time, but that's all really. Because there's no allowing for the kind of random events that are really a feature of every biological process ever. So there's a fairly solid argument, I think, as a biased person who makes stochastic models for a living, that if you're going to model a biological process, particularly population processes, the best model, or the most useful model and the most interesting model is usually going to be a stochastic one. Unfortunately, they also tend to be a little bit more complicated to analyze. So it goes. The other thing I want to point out is that most of the time for stochastic models, depending on the probability distributions you're using, you need to know both the mean and the variance of the randomness you're adding into your system. Particularly the variance matters, because if the variance is large, then your trajectories have more wobbles in them. And one other diagnostic difference between deterministic and stochastic models is that the endpoint of a deterministic model is just that, a single endpoint. Whereas for a stochastic model, your end result is going to be a distribution of possible endpoints. So if I want to know what's going to happen to my model, this one, what's going to happen at n at times t is 100, instead of just getting a value, I'll get a distribution of possible values. Or a distribution of possible outcomes, I should say. So most of what we do when we make stochastic models is analyze those distributions of possible outcomes. In a stochastic population model, there are typically two sources of stochasticity: demographic stochasticity and environmental stochasticity. And I'm going to talk about each of those just for a couple. They're just different ways of putting randomness into your model. Demographic stochasticity is the random change in population size due to random fluctuations in birth or death rate, or rather, random fluctuations in demographic parameters. So demographic parameters are birth rate, death rate, immigration, and emigration. So thinking back to the simple stochastic model of exponential growth, n at times t plus 1 is lambda t times n at t. Remember that growth rate is really births minus deaths. So if I want to include demographic stochasticity in my model, I can make my birth rate stochastic, I can make my death rate stochastic, or I can make both of them stochastic. So if you're actually simulating a stochastic model like this, what you would do would be every time step, draw your birth rate and or your death rate from some probability distribution, and then plug those in and crank the population forward in time. Right, and if you have a fancier model where the growth rate is birth minus death plus immigration minus emigration, you can make any or all of those stochastic as well. By the same method of drawing a value for them from a probability distribution every time step and using that to project the population forward. This kind of variation is roughly analogous to genetic drift, since it's not biased in one direction or the other. So this kind of stochasticity just makes the population wobble around the expected mean of all of the parameters. I'd also like to point you can have stochastic density dependence. Right, in a density dependent model, n at times t plus 1 is n at times t times some density dependence term, lambda times 1 minus n at t over k, for example. So if you wanted to make a density dependent model stochastic, you just take your lambda again and draw it from some distribution where the mean of the distribution is this whole thing, lambda multiplied by some density dependence term. So every time step you actually change the distribution you're drawing from because of the n of t in it. But it's still just demographic stochasticity because it's a random change in our demographic parameter lambda. Environmental stochasticity is just what it sounds like. It's fluctuations in population size driven by environmental changes, or environmental factors, I should say. And if we know anything about the environment, it's that it's a random process. So, environmental stochasticity tends to be more analogous to natural selection, in the sense that you maybe have two different environments. Quite often we'll model things such that there are two different environments, one's good and one's bad. So every year the environment puts selection on your system in one direction or the other. So the changes in the environment are kind of analogous to a fluctuating selection model situation. So for example, let's say I'm monitoring my attempts to grow wildflowers in my yard. So I'm keeping track of the population size of poppies. I'm going to divide my environmental states into either wet years or dry years. So my environments, say we've divided everything into wet years and dry years. And on wet years, I'm going to call wet years good years. And in good years, the growth rate is greater than 1. And in dry years, which are bad, growth rate is going to be less than 1. So depending on the sequence of environments my population sees, it might grow or shrink depending on how many of those years are good or bad and the order in which those occur. So my model would still look like n at times t plus 1 is n at times t times lambda t. But now, lambda is a function of environment at time t. If the environment at time t is good, lambda at t is going to be, or if the environment at times t is bad, lambda at time t will be less than 1. So this defines the stochasticity of my, and we might say that wet years are Poisson distributed. So there's some given probability, right? Every year we define p good year, that's 0.7, and p bad would then be 0.3. So I could use a Poisson process to model my environment, and then use that to update my population size. So in practice, if you're making this kind of model, you start with your initial population size and decide what the distribution of environments will be, and then for each time step, you draw an environment out of the random process, and then use that environment to choose your growth and update the number of individuals. The next year, you draw another environment, which tells you your growth rate, and you can update the population size. Rinse and repeat for as many years as you want. And then do a number of those simulations to get a distribution of the outcomes. It's also entirely possible to have both environmental stochasticity and demographic stochasticity in your model, just like it's quite possible to have a genetic model that has both selection and drift. A little bit about Markov models and Markov chains. All the models I've talked about so far have been Markov models, because the defining property of a Markov model is the Markov property. Markov property is that the future in your model is defined entirely by the present. Having additional information about the past doesn't help you. Which basically just means that n at times t plus 1 is a function of n at times t, right? And only n at times t. If I knew n at times t minus 1, that would give me no information about what's going to happen at n t plus 1. The future state depends only on the present. You can have continuous time Markov processes as well, but the Markov property still holds, is that for any time point in the model, the future is uniquely defined by the past. The future is uniquely defined by the present. These processes are also referred to as being memoryless, in the sense that is whatever happened in the time step before the one you're looking at becomes irrelevant as you try and go forward another step. There's going to be a whole section devoted to Markov models, so I'm just mentioning their existence right now. Another kind of stochastic model you hear talked about is a random walk model, which is an awful lot like what it sounds like. Random walk is a random process model where every time step, the process moves some distance, takes a step that has some distance and some direction, right? And both the step length and its step distance can be random variables. The simplest random walk is a one-dimensional random walk. So we'll walk along the number line. So here's my number line, here's 0. 1, 2, 3, 4, -2, -3. So in a one-dimensional random walk, the process starts at 0. Every time point, you flip a coin. And if it's heads, I go to the right 1 step. And if it's tails, I go to the left 1 step. That's a simple random walk. And as I flip coins, I'll go right 1 step sometimes. I'll go right again, then I'll go back, then I'll go that way. And then maybe I'll go that way, and then maybe I'll get some more tails. And the process will move around randomly. A lot like again, a lot like genetic drift. In fact, one of my favorite random walk models is the Wright-Fisher model of random drift. If you want to model the genetic drift in your population, you start at some allele frequency p, and every time step, the allele frequency changes, basically goes on a random walk. So this drift model is actually both a random walk and a Markov chain. These are both one-dimensional random walks, but you can use multi-dimensional random walks where your directions go beyond up and down, they could be left and right, to model things like foraging behavior and animal movement across a landscape. In order to model a random walk for every time step, right, for each time step of a random walk, you need to choose step length, how far you're going to go on your random walk, and the direction. Are you going to be going, in my one-dimensional random walk, am I going to be going right or left? In a more complicated random walk model, step direction might actually be north, south, east, west, or something fancy like that. So now that we've learned some of the vocabulary of stochastic models and about different kinds of stochasticity, in the homework, you're going to actually go build some of these models and play with them and get a feel for how they behave and how the different kinds of stochasticity change the outcomes of your models. So now that you've been through the modules about stochastic modeling and about matrix modeling in population biology, now we can talk about stochastic matrix modeling in population biology. So we know from before that it can be convenient to put a bunch of information about your population into a matrix to make predicting population sizes into the future easier, if your population is age or stage structured. So let's say you've got some Leslie matrix, and it's got fertilities in the top row, and it's got survivals on the off diagonal. You can project your population, which is a vector of the number of individuals of each age or stage, depending on whether it's an age or stage structured model. Right? So you can project n at time t plus 1 is equal to L times n at the current time step. And if you want to go forward in time 2 time steps, you just multiply by the matrix again, assuming that this matrix of fertilities and survivals is constant. Sometimes I might call these vital rates. In demography, fertility, survival, and growth are things like vital rates. It sounds kind of Victorian to me, but anyway, that's what they are. So if your vital rate matrix is constant over time, you can keep doing this projection, and at times t plus 3 is L times L times L times n at t, so that eventually you get n at any times t is L raised to the power t times n at when you start it. This is all well and good if the vital rates that describe your population are constant in time. Most real populations live in an environment that is a big source of stochasticity and randomness. For a plant population, say, fertility rates might be much higher in years where there's more rain. So you might have wet years and dry years with higher or lower fertilities, and then the distribution of wet and dry years will change a lot about how your population's size is going to change over time. So for cases where vital rates are a function of the environment, or the environment is variable, we have a whole edifice of stochastic matrix models to try and understand how population dynamics work in a variable world. Okay, so let's say you want to build a stochastic model with variable environments. First thing you need to do is define some set of possible environments such that each environment has a unique matrix of vital rates. Environment has its own set of the vital rates, i.e. matrix. Each environment has a matrix. Then you need to define the rules governing the sequence of environments your population is going to encounter. So let's go back to my initial idea where there's wet years and dry years. So that's two possible environments. Each one of them is going to have its own unique set of vital rates. Probably in the dry years, survival will be less than it is in wet years, say. So what's going to happen to my population depends on what I decide about the rules governing the sequence of environments. So there's a lot of different ways you can make your environment variable. I'm just going to talk about two of them. So for example, you can have IID environments, independent, which is, I always forget which I is which, independent and identically distributed, which basically just means that the probability of a dry year is constant. So every year there's some probability of getting each environment. If you have more than two environments, each one would have a constant probability of being the environment in a given year. This implies that probability of a wet year is also constant, and it's going to be 1 minus the probability of a dry year. Anyway, so if you're modeling the environment in this way, for every time step in your model, you draw an environment, wet or dry, based on drawing a random number out of a probability distribution, and use the matrix corresponding to that environment in your projections. The other common way to do this is to have Markovian environments. This seems a little bit more realistic because it means that the probability of a dry year is some function of last year's environment. So maybe if last year was a dry year, that means the probability of having a dry year again this year is higher than it would be if last year was a wet year. And we have a whole section about Markovian models and Markov chains elsewhere. So no matter what rules you use to decide how your environment is going to be variable, the guts of the model is always going to be the same. For n at time t plus 1, where n is your vector of the number of individuals in each stage or age class, you're going to project forward based on some matrix of vital rates times whatever the population vector was at that time. And you're going to draw these. The matrix you use, x at t, is going to depend on the environment you drew at t. And after lots and lots of time steps, instead of what we saw for the deterministic case, this time, now n at t is actually just a big product of all of the x at t times n0. And it's the product from I is equal to 1 to t. So just to make sure I'm being clear, I'm going to write down a little bit of pseudocode, so just pretend that I'm making a simulation of one population trajectory for my population that's got wet and dry years. So I'm going to say the probability of a dry year is always going to be 0.5. It's always 50-50 shot whether you get a wet or a dry year. So if I want to simulate what's going to happen to my population after 100 years in this kind of environment, then I'll have to say define two matrices, x dry and x wet, and my initial vector of population. How many individuals in each stage I have. So then if I want to simulate it, I can say for t is equal to 1 to 100, the first thing I do is I decide what kind of environment I have. Since I'm using IID environments and I know that the probability of dry is 0.5, I can just draw a random number. Random number is using whatever random number generator you have. And then if the random number is greater than 1/2, environment is dry, in which case x at time t is going to be, we're going to use x dry. Right? Otherwise, x at t is going to be x wet. And so now that I've decided my environment, which decides my matrix, then I can say n at t plus 1, or I guess, given the way I've written this loop, n at times t is equal to x at t times n at t minus 1. Right. If you rinse and repeat and do that 100 times, your population will get projected forward based on a random series of environments x at t. Right. So you could do it this way. Or you could kind of simplify your life and just fill a vector with 100 random numbers, and then for each space in that sequence of random numbers, turn that into a sequence of environments and turn it into a sequence of x at t. So you would just have 100 matrices in order. So in a different color now, right? You've got a sequence of 100 matrices, some combination of dry and wet in order, and you can just calculate n at time t. It's going to be the product of x at times t times x at time t minus 1 times x at t minus 2 all the way back to x at time 1 all times n at time 1, which is what I meant before when I said it's just the product of all the environments times the original population. So if you're doing a computer simulation, you can just generate this sequence of environments and a sequence of matrices, do the multiplication, and find out what your population size is going to be. These two methods will give you the same result. But for what we're going to get to a little bit later on, it's important that you be able to think about this as actually being the result of a big product of matrices. Another important thing to consider here, because now we're doing stochastic models, is that this bit here, n at time t is equal to this big product, this represents one population trajectory. And since the x at time t come out of a random process, if I do just one of these, it's going to give me an example instance of my population, but it's not going to tell me everything I need to know about the population dynamics. Because if I do several of these simulations, they will all have slightly different outcomes. So, one of the most interesting things about a stochastic simulation is how variable your simulation runs are from each other. So if I was going to actually try and make this model, I wouldn't just run one 100-year-long simulation. Right? I would say, right, for simulation 1 to 100, I'd do 100 of them probably more actually. right? But for some large number of simulations, make multiple trajectories so that you can compare them and get an idea of the variation within and between your simulation runs. Okay, so let's say now I've run my simulation runs. I've projected my population forward through 100 years of wet and dry years, and I've done 100 replicate simulations, so I have 100 different population trajectories, and I want to start to calculate useful stuff about my system based on those simulation outcomes. The two most important measures from a population model like this are the stochastic growth rate and its variance. So for the deterministic case, right, the long-term population growth rate was lambda, which is n at times t divided by n at times t minus 1. Right, the long-term deterministic growth rate, which you got from the dominant eigenvalue of your vital rate matrix. So in a stochastic model, every time step is going to have a different one. So each of your environments at time t is going to give you a matrix of vital rates at time t, which is going to give you a different single-step growth rate at time t. You can get a measure of the stochastic growth rate, which I'm going to call A. It's going to be an average. It's going to be an average over all simulations and all time points of the single-step growth rates, right? So for any given simulation path, you're going to have however many time steps worth of single-step growth rates, and you add all of those together. And then you're also going to have, over all of the different simulations, add all of those together, divide by the total number of time steps you had and simulations you had, and you get the overall average growth rate across all of your simulations, and that's the stochastic growth rate. And I almost forgot, because I usually forget, we want to take the log of this whole business, because stochastic growth rate A is actually taken to be analogous to R, right? R is the log of lambda. So the stochastic growth rate, which is the stochastic equivalent of R, is the log of this average of all the growth rates across your simulations. Another way to say this is to define the stochastic growth rate to be 1 over simulations and time, to be the average of the total population change, which is usually given by big lambda at t, where big lambda is n at times t divided by n at times 0. So it's the total population growth rate, or not a rate, it's the total population growth. So it's going to be the sum of the total population growth at the end of the simulation for each simulation divided by how long the simulation was. Because the total growth in the whole simulation divided by t is going to give you the average growth within the simulation. If you sum those up across simulations, you get the same answer as you get over here. It's just two different ways of looking at it, whether it's total growth divided by time or single-step growth rates divided by simulations. And the other thing we're interested in is how variable our simulations are in between trajectories. Right? If I do 100 simulations, what's the variance between the total growth in each one, this total growth number? Because in some simulations, there might be a lot of crappy years, and so total growth is quite small. In other years, you might get a run of good years and have total growth be very large. So there's going to be variance in between the different simulation runs in this population growth. So that variance is going to grow the longer your simulations are. Because for a short simulation, there's a limit to how variable they can be, as to how far away from each other the different trajectories can get. Let me just draw a little cartoon here. Right, if this is time, if I've got one population and they all start here, and one of them's doing really well, one of them doesn't do so well, one of them doesn't do so well, one does okay. If I take a slice through my population here, where t is relatively small, the variance between these numbers is going to be pretty small. If I look out here, where the populations have had more time to diverge from each other by random chance, the variance out here is going to be bigger. So the variance I'm talking about calculating down here is actually the rate at which this variance between trajectories grows with t. So we calculate as that over all the simulations and all of the time points. It's the variance, or the sum of squared differences, I should say, between the log of total population growth in each simulation minus the length of the simulations times the average growth. So I call this the average growth because it's the average growth rate multiplied by the length of the simulations. So if all of my simulations give me exactly the same trajectory, this number, the average growth rate times the simulation length, should be the same as the total growth in each individual simulation. So if there was no variance in between these trajectories, this number would be zeros. So now that we've talked about stochastic growth rate and variance, I want to go into a little bit about sensitivity analysis. So when we talk about the sensitivity of a model to some change, what we really mean is how much is the outcome of the model going to change after I make the change to the model parameters. Put in more matrixy terms, if I have my stochastic system where there's wet years and dry years, and survival is lower in dry years than in wet years, maybe I want to know what will happen differently if survival improves in dry years, or if survival improves everywhere. So we say the sensitivity of the stochastic growth rate to changing one of the vital rates, to changing survival, is a measure of how much the stochastic growth rate will change if we change survival a little bit. And it might be really useful to know how sensitive our model is to changing survival or fertility, especially if it's conservation management and you might be actively trying to improve survival or fertility. So you know how much of a change to the population growth rate you can make if you improve survival of juveniles a certain amount, say, for example. So let's talk about how to get numbers for that in this stochastic matrix context. First, I'm going to define a couple of terms for myself. I'm going to call my baseline matrices, the ones from before, x dry and x wet. And I'm going to define a perturbation matrix. And I'm going to call it H. So H is going to look, let's say, these were 3 by 3, oops. Let's say this is what my X matrices look like. If I only want to change this one, fertility of 2-year-olds, then H is going to be zeros everywhere except for the element I'm interested in. So I'm interested in what happens if we perturb the original matrices by changing second-year fertility. Just for example. You might be perturbing more than one thing at a time, but just it's easiest to understand if I want to calculate the sensitivity to making this change, then this perturbation matrix contains the change. It's only going to be 1 there and zeros everywhere else. So that means that after the perturbation, x dry star is going to be the original x dry matrix plus some small number s times h, the perturbation matrix. So s is a measure of how big a change I'm making to this element, and it's usually small because we want to know, we think of sensitivity as being kind of like a derivative. What happens if I make an infinitesimally small change to this fertility? So in this, if we think about it this way, what I'm looking for is the sensitivity of A, my stochastic growth rate, is going to be A if we use the perturbed system, x star dry and x wet dry, minus what the stochastic growth rate would have been if we just used the baseline, divided by s, divided by how big we made the perturbation. So you could actually estimate this by just straight up doing simulations. You could do a bunch of simulations to get the stochastic growth rate under your original system, and then add some small amount of fertility to both of them, redo the simulations, get another estimate of stochastic growth rate, find the difference, and divide by how big the change was, and that would give you an estimate of the sensitivity of A. That's actually really clunky, and there's a better way to do it. But I'm just explaining it this way so conceptually you'll know what a sensitivity is. And you can do the same thing for the sensitivity of the variance. It's just the difference between the variance you get in the perturbed model minus the variance you get in the baseline model, all divided by how big the change was. So I'm going to admit I'm just going to give you the procedure for calculating stochastic sensitivities. If you want to see some good proofs or more discussion of this, I recommend Hal Caswell's book, Caswell's Matrix Population Models book. It's a fantastic resource. Anyway, so the first step is to do the baseline simulations. So, 1, make some big number, m number of simulations of length t using baseline matrices. 2, you can use the sequence of matrices x at time t in simulation M to make sequences of, for each time step in each simulation, use them to make sequences of u vectors at time t in simulation M, which is the stage structure of the population U. You'll remember from the matrix modules, U is one of the eigenvectors in the non-stochastic case. U is the long-term stable stage structure in your population. So these are single time-step stage structures in your population. And you can get those at each time step by multiplying x at time t times the stage structure and the last time step, all divided by the norm of that product. Right, and these are all in the mth simulation. And you also need single-step growth rates for population at time t in simulation M. And for each one, that's just going to be x at time t times the stage structure at time t and their norm. No. So the single-step growth rate is going to be that norm from up here. The matrix at time t in simulation M times the stage structure in t minus 1. And you also need the other eigenvectors, which you get by multiplying v at times t, vt at times t times x at t, divided by their norm, vt at t times x at t. So when I say use the X matrices to generate these sequences, you start with an initial population, an initial stage structure U, and you can use this equation to project your stage vectors forward all the way through the simulation for each simulation. And then you can use those to generate the single-step growths, and you actually go backwards in time. You start at the end of the simulation and go back to time is equal to 1 to generate the VT reproductive value vectors. So now that we have all of our X and U and VTs and lambdas based on the baseline simulations, then we can define our perturbation matrix. So define perturbation. So we're going to say after the perturbation, the population is going to behave as having matrices X star, which are each equal to the original baseline X plus some small perturbation. So for every time step in every simulation, the deviation between the single step growth rate in simulation M at time t using the perturbed system minus the difference between the growth rate in the perturbed system and the growth rate in the original system, the baseline system, is going to be given by this ugly looking expression, Vt at times t times the perturbation matrix at times t times the stage vector at t minus 1 all over this matrix norm times Vt at time t times U at time t. And all of these are for whatever simulation M. So you can calculate the difference between the perturbed system and the baseline system at every time point in every simulation, and the overall sensitivity, right, is just the average of these deviations, because you want to know how different is the outcome going to be between the perturbed and the baseline. So we just sum up all of the individual differences and then take the average. So the sensitivity of the stochastic growth rate is going to be 1 over the number of simulations times the number of time steps in each one, and then the sum over m and t of those deviations above. And the sensitivity of the variance ends up being 2 over the number of simulations, and it's a product of the difference between the stochastic growth rate from a single simulation and the overall stochastic growth rate times the sensitivity of the stochastic growth rate based on a single simulation minus the sensitivity of the stochastic growth rate based on all of the simulations. So what you end up with after doing this kind of calculation depends entirely on what you chose your perturbation to be. A very standard thing is to say your perturbation is a small increase to any one of the given vital rates. So if I decided my perturbation matrix, like I said before, was a small increase to fertility of 2-year-old individuals, then after doing all of this messy vector matrix stuff, you end up with a measure of how much larger or smaller the stochastic growth rate would be if fertility was that much bigger in every environment. So I should also point out, these are estimators, but as you make the number of simulations and the number of time steps bigger, these get more and more exact. So if you make them big enough, they become essentially exact measures of the sensitivity of the system's growth rate and variance to any perturbation you want to make to your vital rate matrices. So I know that last bit about calculating sensitivities was a bit of a mess. If you're doing it with MATLAB or with R, it's actually really straightforward to generate those sequences of vectors and matrices, so do not despair. It just looks bad on paper. And the applications of stochastic models and stochastic sensitivities are many and varied, but mostly, since this is about models with environmental variation, these kinds of models are really great for answering questions about what will the effect be of a change, of a consistent change in environments. What will happen if the frequency of dry years increases? What will happen if we increase fishing quotas? Fishing or hunting. So in that case, you might have a stage-based model of your population, and you can decide that an increase to fishing or hunting would mean a decrease in survival of whatever life stage it is that you hunt or fish, and you could project how much will that affect population growth rate. If I start fishing out fish that are, if I start allowing people to catch fish that are smaller from a more juvenile, is that going to have a bigger effect on population growth rate than if we just fish out the big fish, all that kind of stuff. And in more age-based models, you can say what'll happen if we keep improving infant mortality. Right? If we keep improving infant mortality, which hopefully we will, how much faster will the human population grow? Or how many more old people will there be in 2050 if we keep improving survival of disease in old age? These are all the kinds of questions you can answer with a sensitivity analysis of a stochastic model. And again, this is one of those ones where stochastic matrix models are a huge subject all on their own, and I just went through maybe 20 minutes. So if you're interested in age and stage-based models which come up quite often in ecology and demography, I recommend Hal Caswell's book, and Tulja, our other instructor, wrote a book in 1990 that has some really great derivations of some of the classic results in demography and age stage-based models. So I'm going to say that again. See Caswell's book. It's a bit of a tome, but it's very useful.
Please consider subscribing to two excellent channels about IT, Avocodus and Ave Tech. Avocodus is a great channel with programming tutorials and IT humor, and Ave Tech is about the stories behind tech and business. Links are in the description. Thank you.